Listen closely. I'm not going to take much of your time, but what I'm about to share could fundamentally change the way you see the universe and our place within it. For thousands of years, humanity has gazed at the stars, wondering if we could ever touch them. And today, I want you to imagine something extraordinary. The next leap in human space travel will not be merely a rocket launch. It will be a revolution in thinking, a transformation in technology, and a bold redefinition of what it means to explore. The stars are no longer distant points of light. They are destinations waiting for us to reach them. For over a century, human beings have relied on chemical rockets as the primary means of reaching space, and while they have achieved extraordinary milestones, this method is inherently limited. Rockets, as powerful as they are, operate by controlled explosions, a burst of energy that propels a spacecraft beyond Earth's atmosphere, but consumes vast quantities of fuel and discards most of the vehicle after a single use. This approach worked to carry humans to the moon, launch satellites, and even send probes to distant planets, but it is inefficient and ultimately unsustainable for long-term exploration. Chemical propulsion confines us to short bursts of motion, brief accelerations that must overcome the immense pull of gravity in a short span of time, leaving us dependent on massive fuel reserves, repeated launches, and careful timing. It is as if we are attempting to cross an ocean with small bursts of rowing. Rather than building a vessel capable of continuous, smooth travel, the next giant leap in space exploration, therefore, requires abandoning this brute force mentality and embracing propulsion methods that are more precise, continuous, and adaptable. Plasma engines, ion drives, and nuclear propulsion offer alternatives that can sustain thrust over long periods, allowing spacecraft to gradually accelerate to incredible speeds without the extreme inefficiency of chemical rockets. Instead of relying on explosive force, these engines manipulate energy and particles in a way that produces constant motion, harnessing the subtle laws of physics to propel humanity farther than ever before. The key realization is that space is a vacuum, and in a vacuum, even the smallest consistent push applied over time produces astonishing results. By moving away from short, violent bursts of acceleration and adopting continuous propulsion, spacecraft can travel farther, explore more, and operate for extended durations without being constrained by the immense limitations of chemical fuel. The implications of leaving the rocket age behind extend far beyond efficiency and speed. They redefine the very nature of space travel itself. Chemical rockets impose strict schedules, limited cargo capacities, and extremely high costs per launch, making exploration rare and episodic. With continuous propulsion systems, missions become longer, more ambitious, and more flexible, allowing spacecraft to adjust trajectories over months or years, to explore multiple destinations in a single mission, and to endure the harsh environment of space with a reduced need for resupply. This opens the door to exploration of regions that were previously unreachable, the outer planets, the asteroid belt, and even interstellar space. The difference is profound where a chemical rocket moves in short bursts and requires frequent intervention. Continuous propulsion allows motion to be sustained and cumulative, turning a slow journey into a voyage that can ultimately traverse light years in principle, constrained only by energy and ingenuity. This approach also forces us to think about spacecraft not as disposable tools, but as long-lived platforms capable of operating autonomously and continuously, a shift that changes engineering principles, mission design, and long-term strategy. The very way humans conceive of space travel transforms, moving from isolated expeditions to ongoing, evolving exploration. No longer is the objective simply reaching a distant point. The objective becomes continuous presence, observation, and adaptation. By harnessing the subtleties of physics and developing technologies that exploit the vacuum of space rather than fight it, humanity begins to approach interstellar distances with a methodology that is elegant, scalable, and profoundly effective. Simultaneously, this shift in propulsion directly enables the second critical transformation, making space travel routine. At present, launches are dramatic, rare events, often celebrated with immense fanfare. They are expensive, high risk, and largely one-time affairs. But when propulsion becomes efficient, reliable, and capable of extended operation, the economics of space travel change. Reusable spacecraft, orbital refueling stations, and automated maintenance systems all contribute to a scenario where launching into space is no longer a historic occasion but an everyday activity. The democratization of space follows naturally from this technological shift. As costs drop and reliability increases, more organizations, scientists, and even private individuals can access orbital and interplanetary travel. The comparison is striking. Air travel was once a miracle, a journey few could imagine undertaking. Today, it is routine, predictable, and accessible to billions. Space is poised to follow the same trajectory. The frequency of launches will increase not linearly but exponentially as each success reduces risk and cost, creating a feedback loop that accelerates innovation and exploration. Routine access to space also transforms the psychology of exploration. When launches are rare, human ambition is constrained. Missions are planned conservatively, limited by resources, risk, and opportunity. Once travel becomes routine, humans begin to think differently about exploration itself. Strategies can shift from immediate survival to long-term development. Settlements, resource extraction, scientific observation, and industrial activities can be planned with decades in mind rather than years. Students grow up witnessing human activity in orbit as part of everyday life, cultivating a generation of engineers, scientists, and explorers who inherently understand space as accessible, not distant. The presence of humans in orbit becomes normalized, shifting cultural perceptions and expectations. Humanity begins to perceive space not as an unreachable frontier, but as an extension of our world, a medium in which civilization can expand and operate. In addition, routine travel enables the creation of infrastructure that multiplies the possibilities of exploration. Orbital stations evolve from temporary habitats into permanent hubs, serving as factories, research laboratories, and staging areas for deeper missions. Fuel depots in orbit allow spacecraft to be refueled without returning to Earth, enabling longer journeys and more complex trajectories. Automated maintenance systems and robotic assistance ensure that spacecraft and stations remain functional with minimal human intervention. Each new piece of infrastructure reduces risk, increases efficiency, and opens the door to further expansion. What begins as a technological improvement quickly becomes a cultural and economic revolution. Space transforms from a rare destination into a system in which human ingenuity, commerce, and science coexist and reinforce one another. The cumulative effect is profound. As propulsion improves and travel becomes routine, humanity transitions from being a species that occasionally visits space to a species that inhabits it continuously, sustainably, and with growing sophistication. Every mission, every innovation, and every leap in efficiency compounds to create a civilization increasingly capable of extending its presence throughout the solar system and eventually into interstellar space. For much of human history, the idea of living beyond Earth belonged entirely to imagination, mythology, and speculation. The moon was a distant symbol, Mars a point of fascination, and the stars merely pinpricks of light scattered across the sky. Yet the moment humans first left the surface of Earth, even briefly, something fundamental changed. For the first time, we could see our planet as a small, fragile world floating in a vast cosmic ocean. That perspective transformed our understanding of what it means to survive, to expand, and ultimately to explore. Becoming a multi-planet species is not an act of vanity or escapism, it is an extension of the most basic strategy of life itself. Life, if it is to endure, spreads, it migrates, it adapts. And humans, being the species capable of conscious foresight, can now direct that expansion intentionally. The first steps in this process are deliberate and methodical. We begin close to home, learning to adapt, survive, and thrive in environments that differ radically from Earth. The moon becomes our training ground, not as a final destination, but as a laboratory for life beyond our home planet. Here, we learn how to extract water from regolith, generate energy in extreme temperature cycles, build habitats from local materials, and maintain life support systems in an environment hostile to human biology. Each lesson is incremental, but together they form the foundation for expansion to Mars and beyond. Every failure teaches resilience, Every innovation reduces risk, and every experiment conducted on the moon prepares humanity for the challenges of interplanetary life. Mars represents the next threshold, a world that is distant enough to test human adaptability yet familiar enough to feel achievable. Unlike the moon, which requires minimal travel time, Mars demands months of continuous journey through radiation-filled space, microgravity, and isolation. Establishing a permanent presence there will redefine our relationship with survival. Earth alone is a fragile cradle. Catastrophes, whether asteroid impacts, pandemics, or climate instability, threaten life in ways that a single planet cannot endure. By establishing colonies on multiple worlds, humanity spreads risk and increases its chances of long-term survival. Beyond the practical necessity, multi-planet colonization opens a remarkable possibility: human evolution in new environments. Gravity, atmospheric composition, radiation exposure, and day-night cycles differ from those on Earth, subtly shaping biology, physiology, and even culture over generations. Adaptation may produce humans capable of surviving on Mars with ease, individuals genetically, physiologically, and culturally attuned to life beyond Earth, expanding what it means to be human. Each new colony becomes a stepping stone to further exploration, a platform for experiments that push both technology and biology to the edge. It is not merely about reaching distant worlds. It is about preparing humanity to thrive wherever the universe allows, learning to exist in conditions once thought hostile or impossible. As humanity extends to other worlds, another critical element ensures the success and safety of these endeavors: artificial intelligence. Humans are extraordinary, yet they are fragile. Space is not forgiving, and the environments we encounter are often hostile to our biology. Long before humans arrive, intelligent machines will serve as our scouts, builders, and analysts. They explore dangerous terrain, map planetary surfaces, identify resources, and construct habitats autonomously. They can operate continuously in extreme conditions without fatigue, fear, or error. In deep space, where communications with Earth may be delayed by minutes or hours, autonomous systems become indispensable. They extend human presence by acting as advanced agents, preparing environments for colonization, maintaining life support systems, and mitigating risks that would otherwise endanger human crews. This partnership is fundamental. While humans excel at creativity, intuition, and problem-solving in unpredictable scenarios, machines excel at precision, endurance, and processing massive data sets. Together, they create a hybrid intelligence capable of venturing further than either could alone. Artificial intelligence in space is not merely a tool, but a collaborator in discovery. It allows humans to focus on questions rather than survival. While machines monitor radiation levels, structural integrity, and atmospheric composition, humans can devote themselves to exploration, experimentation, and interpretation of data. Habitats and spacecraft are no longer passive structures, but intelligent systems capable of responding to emergencies, adapting to environmental changes, and even predicting problems before they occur. This capability transforms the psychology of space exploration. Humans feel less isolated, less vulnerable, and more empowered to make bold decisions, knowing that intelligent companions are continuously safeguarding their survival. The collaboration between human creativity and machine reliability accelerates mission success, making colonization and long-duration exploration feasible on scales once unimaginable. The synergy between biological and artificial intelligence will define the next era of space expansion, where humans do not simply survive, they thrive. Beyond practical survival, the presence of AI reshapes the cultural and philosophical dimensions of human life in space. Collaboration becomes the guiding principle not only between humans and machines, but also among humans themselves. Diverse teams across planets must work together seamlessly to manage resources, maintain infrastructure, and solve unexpected problems. National or political divisions fade when survival depends on collective competence and trust. Humanity begins to operate as a unified species, capable of thinking beyond short-term gains, considering multi-generational goals, and cultivating a shared vision for cosmic exploration. This cultural evolution, driven by the necessities of living and thriving in space, will ultimately influence civilization on Earth as well. Knowledge, ethics, and ingenuity developed off-world feed back into terrestrial societies, accelerating innovation, collaboration, and understanding of our planet's fragility and potential. Every colony, every AI-managed habitat, and every successful mission multiplies the potential for discovery. As humans and machines explore moons, planets, and asteroids, they generate data that informs subsequent missions. New insights into planetary geology, atmospheric chemistry, radiation belts, and potential biological markers of life all accumulate, guiding the trajectory of human expansion. The discoveries themselves become a catalyst for technological development. Improved propulsion systems, radiation shielding, habitat design, and resource extraction technologies all emerge from this iterative process. Exploration and innovation feed each other in a continuous loop, accelerating the rate at which humanity can understand and operate in the cosmos. This interplay between human curiosity, technological capability, and environmental challenge transforms space from an abstract frontier into an interconnected laboratory, where every action produces both knowledge and capacity, reinforcing humanity's ability to survive, adapt, and expand. Psychologically, the presence of intelligent systems and collaborative multi-planet communities also alters human perception of risk and possibility, where once fear, limited ambition, knowledge, and preparation replace uncertainty. Humans learn to operate in extreme environments with confidence, gradually redefining the boundaries of what is achievable. As missions become longer, habitats more sophisticated, and AI more capable, the idea of exploring distant worlds becomes not just conceivable but routine. The cumulative effect is a transformation in human cognition and imagination. The cosmos, once distant and intimidating, becomes an arena for participation, creativity, and growth. Each success expands the perceived limits of possibility, encouraging further innovation and more ambitious endeavors. The human mind, supported by intelligent machines and grounded in empirical exploration, evolves alongside the expanding footprint of humanity in space, producing a civilization capable of thriving across multiple worlds while continuously learning, adapting, and advancing. For decades, faster-than-light travel and wormholes were dismissed as fantasies, the whimsical creations of science fiction writers rather than serious physics. The idea of crossing vast cosmic distances in human lifetimes seemed impossible, forbidden by the speed limit imposed by the laws of relativity. Yet, when we examine Einstein's equations more closely, we find a surprising subtlety. They do not forbid the concept of warping space itself. The equations allow space to stretch, contract, and bend, opening the door to possibilities that were previously unimaginable. The notion of a warp drive, or a traversable wormhole, is no longer purely speculative. It remains theoretical, yes, but it is grounded in mathematics and the known laws of physics. What was once considered magical, impossible, or absurd has become a legitimate field of scientific inquiry. The universe is not a rigid backdrop, it is a dynamic fabric responsive to energy and matter, capable of being manipulated in ways that could, in principle, allow distant stars to be reached within human lifetimes. This conceptual shift, moving from impossible to how can we test it, marks one of the most profound changes in our approach to space exploration. It forces humanity to imagine a cosmos not as a distant, unbridgeable void, but as a medium that can be traversed, shaped, and navigated. The implications of such a realization are staggering. If space itself can be manipulated, interstellar travel becomes a question not of endurance or chemical fuel, but of geometry and energy. Imagine a spacecraft not racing through space, but carried along by the motion of space itself, riding a wave in the fabric of the cosmos. Distances between stars shrink, and destinations that once seemed hopelessly far away come within reach. The focus of exploration shifts from brute force propulsion to ingenuity in controlling the structure of space-time. Entire star systems, previously unthinkable to explore, suddenly become accessible, not in centuries, but perhaps in decades. The theoretical constructs of warp drives and wormholes demand immense energy and precise control over exotic forms of matter and negative energy densities challenges that are daunting but not inconceivable. They stretch human imagination and engineering alike, forcing us to rethink the fundamental relationship between matter, energy, and space. This new perspective transforms not only technology but also the very way humanity conceives of its place in the universe. No longer are the stars untouchable points of light. They are reachable destinations, each with its own challenges, opportunities, and potential discoveries. The universe becomes a dynamic laboratory where theoretical physics informs practical exploration, and every observation is an experiment in understanding the cosmos by contemplating the possibility of faster-than-light travel. Humans begin to think beyond the limitations imposed by earthbound experience, recalibrating expectations, ambitions, and strategies. It changes our relationship with time, distance, and scale. We no longer perceive the cosmos as an infinitely remote expanse, but as a navigable arena awaiting exploration with the right combination of mathematics, technology, and ingenuity. The mere act of imagining such possibilities reshapes our aspirations, motivating scientists, engineers, and dreamers to pursue breakthroughs once dismissed as impossible. As humans begin to leave Earth and establish colonies beyond our planet, identity and society itself begin to evolve. National borders, political divisions, and cultural separations lose some significance in the face of shared survival and the logistical challenges of interplanetary life. Cooperation and collaboration become essential, not optional. Habitats on the Moon, Mars, and elsewhere depend on collective effort, coordinated problem solving, and trust between individuals and teams spread across vast distances. The pressures of survival and the necessity of efficiency forge a shared human identity defined less by geography or politics and more by our shared capacity for exploration and adaptation. Cultural evolution accelerates as communities develop new norms, values, and systems appropriate for life in extreme environments. Humans learn to think not just in terms of days or years, but in decades and centuries, considering multi-generational goals and responsibilities. The expansion of civilization into space fosters a broader perspective, one that encourages unity, long-term planning, and an appreciation for both the fragility and resilience of life. The presence of artificial intelligence further amplifies this evolution. Autonomous systems not only ensure the safety and efficiency of habitats, but also support cognitive and operational functions that would otherwise overwhelm human crews. In extreme environments, humans rely on AI to monitor systems, predict problems, and provide critical analysis in real time. This partnership between human creativity and machine precision enhances decision-making, reduces risk, and allows explorers to focus on scientific discovery and adaptation. It also transforms our psychological relationship with space. Isolation and danger are mitigated by intelligent companions capable of responding instantaneously to unforeseen challenges. The combination of human insight and artificial assistance makes long-duration missions feasible, sustainable, and even psychologically manageable. As humans integrate with intelligent systems, the line between biological and technological intelligence blurs, creating hybrid teams capable of operating far beyond the limitations of either alone. The acceleration of discovery is another consequence of expanding humanity beyond Earth. Each new habitat, each exploration mission, and each automated probe provides data that inform the next steps. Observations of planetary geology, atmospheric chemistry, radiation levels, and potential biological markers accumulate into a growing body of knowledge that drives innovation. Scientific understanding and technological advancement reinforce each other. Propulsion methods, energy generation, habitat construction, and life support technologies all improve in response to the demands of exploration. Every success enables new opportunities, every failure teaches critical lessons, and each incremental improvement compounds to create exponential progress. The process is iterative, self-reinforcing, and ultimately transformative, expanding both human reach and comprehension of the cosmos. This extended presence in space also transforms the culture and education of future generations. Children growing up in a multi-planet civilization will experience space not as a distant curiosity but as an accessible environment. They will learn from habitats, AI systems, and colonies as if they were classrooms, observing science, engineering, and adaptation in real time. Education becomes immersive, experiential, and iterative, cultivating creativity, problem-solving skills, and curiosity from a young age. Society shifts its focus from immediate gratification to long-term exploration goals, emphasizing the development of skills, knowledge, and ethical frameworks that sustain interplanetary life. The very idea of what it means to be human evolves, expanding from survival on a single planet to thriving across multiple worlds capable of navigating environments once thought impossible. Technological and psychological evolution proceed hand in hand. Advanced AI systems, autonomous infrastructure, and continuous propulsion not only facilitate survival and expansion, but also reshape human cognition, ambition, and culture. Habitats and colonies become integrated networks of life, knowledge, and energy. Humans learn to operate effectively in extreme environments while maintaining creativity, curiosity, and adaptability. Long-term planning, cross-planetary cooperation, and ethical responsibility emerge as necessary components of survival. As humans venture further, the mind and society evolve in response to the challenges and possibilities of space. The transformation is cumulative, iterative, and profound. Humans are no longer confined to Earth, and their potential is no longer constrained by the limitations of a single environment. Expansion into space drives evolution not only in biology, but also in intellect, culture, and civilization itself, preparing humanity to thrive in ways that were once the domain of imagination and science fiction. As humanity extends its presence deeper into the cosmos, one of the most profound transformations will occur not in technology or engineering, but in the human mind itself. For centuries, space was a distant, untouchable realm, and even the bravest explorers and scientists were constrained by assumptions about the limits of human capability. Fear of the unknown, fear of isolation, fear of catastrophic failure, all of these psychological barriers have historically limited human ambition. The next giant leap in space travel will demand more than better rockets or advanced propulsion. It will require overcoming these internal barriers. Humans must imagine that the stars are not just points of light, but destinations to be reached, mapped, and inhabited. The capacity to envision survival, adaptation, and thriving in environments radically different from Earth is itself a form of evolution. When the human mind accepts the possibility of multi-planet existence, it opens pathways for the development of the technologies, strategies, and social structures necessary to make that existence real. Imagination becomes the precursor to action, and courage becomes the foundation of progress. Without this psychological leap, even the most sophisticated spacecraft remains stationary on launch pads, unrealized potential waiting for human readiness to match technological capability. Psychological adaptation extends far beyond courage alone. Humans are biologically and socially optimized for Earth, not for months or years of microgravity, cosmic radiation, or extreme isolation. In deep space or on distant planets, astronauts experience sensory monotony, temporal dislocation, and a disconnection from the social networks that support mental well-being on Earth. Overcoming these challenges requires a conscious recalibration of human expectation and resilience. It is not enough to build artificial habitats or life support systems. Humans must also cultivate cognitive flexibility, emotional endurance, and the capacity to maintain focus and cooperation under extreme and prolonged stress. Training and simulations prepare astronauts for these conditions, but the true adaptation occurs at a deeper level. The mind learns to operate in an environment that defies everyday earthly logic. Every mission beyond Earth is a laboratory, not only for physics and engineering, but also for psychology and sociology, testing the limits of human cognition and social dynamics in unprecedented ways. As psychological barriers are surmounted, the entire framework of exploration and discovery shifts. Fear gives way to calculated risk-taking, hesitation gives way to initiative, and humans begin to conceive solutions that would have seemed impossible only a generation ago. Habitats are no longer merely protective enclosures. They become adaptive ecosystems integrating robotics, artificial intelligence, and human ingenuity. Propulsion systems are designed not just to overcome gravity, but to optimize energy, precision, and long-duration acceleration. Artificial intelligence, rather than a simple tool, becomes a co-pilot, collaborator, and guide, allowing humans to operate at scales and speeds previously unimaginable. Together, humans and intelligent machines form hybrid systems capable of responding to extreme environments, executing complex operations, and expanding civilization across multiple worlds. This symbiosis extends the reach of humanity, allowing us to thrive in conditions that would have once been fatal, transforming exploration into sustainable settlement and continuous innovation. The partnership between humans and intelligent systems also reshapes the social and cultural fabric of spacefaring civilization. Living on multiple planets, humans must operate collaboratively across vast distances, sharing resources, knowledge, and decision-making processes. Political, cultural, and national boundaries become less significant when survival and progress depend on global or interplanetary cooperation. New systems of governance, resource allocation, and ethical decision-making emerge, guided by the necessity of maintaining life in extreme environments. Cultural evolution accelerates, producing norms, values, and priorities suited for interplanetary existence. Humans begin to see themselves not as citizens of individual nations, but as participants in a shared multi-planet civilization. This shift in perspective influences not only life in space, but also life on Earth, as principles of cooperation, long-term planning, and resilience feed back into terrestrial society. As humanity spreads through the solar system and eventually into interstellar space, the rate of discovery accelerates exponentially. Every mission, every probe, and every habitat generates data that informs subsequent exploration. Observations of planetary surfaces, atmospheres, magnetic fields, radiation belts, and potential biological markers accumulate into a rapidly expanding body of knowledge. Each insight drives technological innovation, informing propulsion design, life support systems, habitat construction, and resource extraction methods. The iterative process of exploration and discovery creates a self-reinforcing cycle. Knowledge enables new missions generate more data, and each cycle expands human capability and understanding. This accelerated discovery transforms space from a distant frontier into an interconnected laboratory where human ingenuity, artificial intelligence, and environmental challenges continuously interact to advance both technology and understanding. Exploration becomes not a series of isolated achievements, but a cumulative process that expands the reach and sophistication of civilization. The expansion of human civilization into space also profoundly transforms education and cultural development. Children and young adults growing up in a multi-planet context experience space not as a distant concept, but as an everyday reality. Habitats, colonies, and intelligent systems become immersive classrooms, teaching engineering, physics, biology, and problem solving through lived experience. Education becomes experiential, iterative, and deeply integrated with real-world exploration. This fosters creativity, innovation, and resilience from an early age, cultivating generations of humans equipped to operate in extreme environments and to continue expanding civilization across the stars. The perception of possibility shifts. What was once extraordinary becomes achievable, inspiring further ambition and accelerating the pace of progress. Human identity itself evolves, encompassing not just terrestrial existence, but the capacity to thrive across multiple worlds. The integration of technological, psychological, and cultural adaptation produces a civilization capable of sustained interplanetary and eventually interstellar expansion. Advanced AI systems, autonomous infrastructure, continuous propulsion, and human resilience interact to create an ecosystem of exploration and habitation. Humans learn to operate effectively in extreme conditions, while their cognitive capacities expand to accommodate multi-generational planning and multi-planet coordination. Habitats and spacecraft evolve into intelligent, adaptive environments that protect life, extend capability, and enable creativity. Decision-making becomes informed by real-time data, predictive algorithms, and collaborative intelligence, allowing humans to solve problems that would have previously been insurmountable. The feedback loop between exploration, discovery, and technological innovation accelerates human expansion, transforming the universe from an intimidating void into a navigable domain of opportunity. Psychologically, this evolution reshapes human ambition and perception. Fear and hesitation give way to calculated risk-taking, curiosity, and exploration. Humans learn to perceive extreme environments not as threats, but as opportunities, adapting to challenges and turning limitations into advantages. Space becomes a canvas for human ingenuity, where survival, creativity, and discovery intertwine. Civilization evolves to operate across scales and distances once unimaginable, extending presence, knowledge, and culture to planets, moons, and eventually stars. The boundaries of what it means to be human expand alongside the boundaries of exploration. Every mission, every habitat, and every AI system contributes not only to survival but to the transformation of human thought, capability, and culture. Humanity moves from being a species confined to one planet to a civilization capable of thriving, innovating, and evolving across multiple worlds. As we reflect on the incredible journey humanity is about to undertake, it becomes clear that the next giant leap in space travel is not just about rockets, propulsion, or distant planets. It is about the evolution of human thought, courage, and collaboration. Every advancement in technology, every step into the unknown, and every partnership between humans and intelligent systems brings us closer to becoming a multi-planet species. The universe, once distant and intimidating, transforms into a vast arena of opportunity where curiosity, creativity, and resilience define our progress. By embracing innovation, exploring fearlessly, and expanding our consciousness, humanity will not only survive but thrive among the stars, reshaping the very essence of what it means to be human. Thank you for joining me on this journey of discovery. Your curiosity, passion, and imagination are what drive us forward, and together we can continue to explore the infinite possibilities that await us in the cosmos.